This episode is brought to you by Cisco Educational Premium. For ages, it has been said that mathematics is the mother of all sciences. All the concepts of science stem from mathematics. This alma mater, the nourishing mother, mathematics is truly astounding. And what better concept to demonstrate this than the birth of light as a consequence of solving Maxwell's equations? Maxwell's equations are 4 in number. The first is the Gauss law for electricity, which relates the net electric flux to the net enclosed charge. The second is the Gauss law for magnetism, which relates net magnetic flux to the net enclosed charge. The third is the Faraday's law, which relates induced electric field to the changing magnetic flux. And the last but not the least is the Ampere-Maxwell law, which relates induced magnetic field to the changing electric flux and to the current. But wait, Caleb. What they call Maxwell's equation again? That's a story for another day. Now, the real deal. This is a math show. We're not going to just make sense of statements, but crucially piece together reality from numbers, from mathematics. No shortcuts. These are Maxwell's equations in their differential form. In a vacuum, when there are no electric charges and currents, our Maxwell's equations will evolve to as shown. Our equations are now simpler. The first and the second equations are the divergence of electric and magnetic fields. These two are telling us that if there are no charges present to create magnetic and electric field lines or terminate them, there will be no divergence. The fields will be continuous. They will not start or end. Astonishingly, Maxwell's equations, even in completely empty space, can define and allow the existence of magnetic and electric fields. The other two equations deals with how these continuous electric and magnetic fields behave. The third tells us that the electric field can be created by firings of magnetic fields in the vicinity. Same as the third, the fourth equation tells us that we can get some magnetic fields in the vicinity by firings of magnetic fields. Both of these fields must be at right angles to one another for one of these fields to generate the other. Say in the third equation as shown. Remember mathematically, the left hand side of this equation, del cross E, we are taking the curl of this. We are taking the cross product. Any factors within the cross product will always be completely at right angles to the resultant factors, which in our case is the magnetic field. So if the electric field points anywhere in the xy plane, the magnetic fields must be at right angles to it. The same thing goes for the fourth equation. Any change in the electric field causes new magnetic field at right angle to the electric field. Remember, we are solving Maxwell's equations. Now I want to find electric and magnetic fields formulas, so that when we substitute the left hand side, it will match the right hand side of these equations. We want the third and second equations. Remember, we can't get information about electric field without knowing the value of the magnetic field, and we can't get any information about the magnetic field if we do not know the value of the electric field. So what gives? These equations seem to be conjoined and tangled, so to speak. In math talk, we can say that it is a first order coupled differential equation. What we want to do is to decouple these equations so that they will be completely separate equations. A separate equation for E and a completely separate equation for B. Decoupling them, so to speak. Now, let us start with the fourth equation. Let us take the curl of both sides of this equation, and so we get as shown. On the left side, let us use the factor identity, so we get as shown. On the right hand side, let us exchange the order of the derivatives. Now replacing del cross E using the third Maxwell's law, we get as shown. Now combining everything, if you didn't notice, we have successfully decoupled the two equations into a second order linear partial differential equation. Just to review, the left hand side is the Laplacian operator, del square B, which is a factor 2, same as the right hand side, ignoring mu naught and epsilon naught, we have as shown. And so since both sides are factor quantities, the x component of the left hand side must match that on the right hand side. The y components must match too. Same goes for z. Just to remember, we are now finding the solutions to the second order decoupled differential equation. As we had seen, these really three separate equations. One for x, one for y, and one for z. Now we are going to try some functions on how they will solve our equations. Not that we are trying trial solutions for the x component, which is just the same for the y component, and so for the z component. Now I want to look for a function f that might obey the equation as shown, with alpha just a constant. Say partial sub t square f was just proportional to the original f, and similarly for partial x square f, we want to look for a function whose second derivative is equivalent to the original function apart from e to the x, so to say. Can you remember any? Yes, any cosine or sine function fit here. Partial t square cos t is equivalent to negative cos t. We are going to allow for f to have both an amplitude and frequency. F is equivalent to a cos omega t, where we have omega to be the angular frequency in radians per second. So if we have partial x square bx to be as shown, and if both partial x square bx and partial t square bx are proportional to bx, then we are on the right track. We know that partial x square a cos omega t is equivalent to 0. So we need to add some spatial dependence, some x, so to speak. We are going to propose an ansatz, a trial solution, so to speak. For those who took differential equations classes, I know this word, ansatz, went on top of our heads. It's just an example solution, a trial solution. The product of a function that depends only on space times a different function that depends only on time. Looks like the good old chain rule is in our favor. If partial x square fx is proportional to fx and partial t square gt is proportional to gt, that is, they are sine and cosines, then we have partial x square bx as shown. Also, partial t square bx as shown. And so we see that partial x square bx is proportional to partial t square bx, which is exactly what we need. Now let us consider these two functions, our separable solutions. F is the frequency that is waves per seconds. K is the number of waves per meter. You can think of Kx as the spatial frequency analogous to Ft, which is the time frequency. Now calculating the derivatives of our two functions. we have partial x square fx and partial t square gt as shown. And so if our magnetic field is expressed as bxxt as shown, provided by our answers, then we have partial x square bx and partial t square bx as shown. But let's just check. Our guess bxxt is as shown with partial x square bx to be as shown. So it's okay. And so now we need to ask ourselves, does this obey the second order linear partial differential equation resulting from Maxwell's equations? Is partial x square bx as shown? Now replacing partial x square bx and partial t square bx with the expressions as shown, but the left must match the right. So cancelling terms, we get as shown. And so the question we need to ask, does our ratio match the actual numbers of mu naught epsilon naught and the units? Then those are the exact functions that are gonna solve Maxwell's equations. Now let us just look at the units of the ratio f on k as shown. This means that our f on k represents a velocity. Isn't it incredible? And so letting f on k be equivalent to v, then our equation will be satisfied when f on k square is equivalent to v square, which is equivalent to 1 on mu naught epsilon naught. Then what is the exact value of v? We know that mu naught is the permeability of free space, a magnetic constant, and it has a defined value. And epsilon naught is a dielectric permittivity of free space, and it too has a determined value. And so we are able to find the value of v, and we find it to be 2.998 times 10 raised to 8 meters per second, which is what? Which is the speed of light. This is the solution to the Maxwell's equations. The speed of light is the solution to the Maxwell's equations. The only solutions to Maxwell's equations have the property that they propagate at the speed of light, which are combination of magnetic fields and electric fields orthogonal to one another, carrying with them energy at that specific velocity, which is the speed of light or any electromagnetic radiation specifically. It is not only light that travels at that speed, all electromagnetic radiation specifically. And so James Clerk Maxwell created light, at least mathematically. Whether this was just a coincidence or a deliberate attempt, it doesn't matter. What matters is that it is correct. Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So how do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals. This episode is brought to you by Cisco Educational Premium. Did you know the wave equation is a partial differential equation? The wave equation is a second order linear partial differential equation for the description of waves or starting wave fields as they occur in classical physics, such as mechanical waves like water waves, sound waves, and seismic waves, or electromagnetic waves including light waves. It arises in fields like acoustics, electromagnetism, and fluid dynamics. Single mechanical or electromagnetic waves propagating in a predefined direction can also be described with the first order one-way wave equation, which is much easier to solve and also valid for inhomogeneous media. The two-way wave equation is a second-order partial differential equation describing waves, including traveling and standing waves. The latter can be considered as a linear superposition of waves traveling in opposite directions. The scalar wave equation describing waves in scalars by scalar functions u is equal to u x1 x2 to xn t over time variable t, a variable representing time, and one or more spatial variables x1, x2 to xn, variables representing a position in a space under our look. While there are other factor wave equations including describing waves in factors such as waves for electrical field, magnetic factor potential, and elastic waves. By comparison with vector wave equations, the scalar wave equation can be seen as a special case of the vector wave equations. In the Cartesian coordinate system, the scalar wave equation is the equation to be satisfied by each component for each coordinate axis, such as x component of the x-axis of a vector wave without source of waves in the considered domain, space and time. For example, in the Cartesian coordinate system for Ex, Ey, Ez as the representation of an electric vector field wave E in the absence of wave sources, each coordinate axis component Ei, I is xyz, must satisfy scalar wave equation. Other scalar wave equation solutions U are for physical quantities in scalar such as pressure in a liquid or gas, or displacement along some specific direction of particles of a vibrating solid away from their resting equilibrium positions. The scalar wave equation states that at any given instance, at any given point, the way the displacement accelerates is proportional to the way the displacement changes are squashed up in surrounding area. Or in even simple terms, the way displacement gets pushed around is proportional to how pointy the displacement is and vice versa. Using the notations of Newtonian mechanics and vector calculus, the wave equation can be written more compactly as U as shown, where the double dot on U denotes the double term derivative of U. Del is an upper operator. Del square is equivalent to del dot del is the spatial Laplacian operator, not vector Laplacian. An even more compact notation sometimes used in physics is as shown, where all operators are combined into the D'Alembert operator, not by a box. You see there is a box U is equivalent to 0. So that box denotes all operators that are combined into the D'Alembert operator. A solution of this two-way wave equation can be quite complicated, but it can be analyzed as a linear combination of simple solutions that are sinusoidal plane waves with various directions of propagation and wavelengths, but all with the same propagation of speed c. This analysis is possible because the wave equation is linear and homogeneous, so that any multiple of a solution is also a solution, and the sum of any two solutions is again a solution. This property is called the superposition principle in physics. The wave equation alone does not specify a physical solution. A unique solution is usually obtained by setting a problem with further conditions such as initial conditions, which prescribe the amplitude and phase of the wave. Another important class of problems occurs in enclosed spaces specified by boundary conditions, for which the solutions present standing waves or harmonics, analogous to the harmonics of musical instruments. The two-way wave equation describing a standing wave field is the simplest example of a second-order hyperbolic differential equation. It and its modifications play fundamental roles in quantum mechanics, in continuum mechanics, quantum mechanics, plasma physics, general relativity, geophysics, and many other scientific and technical disciplines. In the case that only the propagation of a single wave is predefined in a predefined direction is of interest, a first order partial differential equation, one-way wave equation can be considered. The wave equation in one space dimension can be written as partial square u on partial t square is equivalent to c square partial square u on partial x square. This equation is typically described as having only one space dimension x, because the only other independent variable is the time t. Nevertheless, the dependent variable u may represent a second space dimension. If, for example, the displacement u takes place in y direction, as in the case of a string that is located in the xy plane, the wave equation in one space dimension can be derived in a variety of different physical settings. Most famously, it can be derived for the case of a string that is vibrating in a two-dimensional plane, with each of its elements being pulled in an opposite direction by a force of tension. Another physical setting for derivation of the wave equation in one space dimension utilizes Hooke's law. In the theory of elasticity, Hooke's law is an approximation for certain materials, stating that the amount by which a material body is deformed, the strain, is linearly related to the force causing the deformation, that stress. The wave equation in the one-dimensional case can be derived from Hooke's law in the following way. Imagine an array of little weight of mass m interconnected with massless springs of length h. The springs have a spring constant of k. Here, the dependent variable ux measures the distance from the equilibrium to the mass situated at x, so that ux essentially measures the magnitude of a disturbance, that is the strain, that is traveling in an elastic material. The force exerted on the mass m at the location x plus h are shown. The equation of motion for the weight at the location x plus h is given by equating these two forces. If the array of weights consisting of n weights spaced evenly over the length L is equivalent to nh, of total mass m is equivalent to nm, and the total spring constant of the array k is equivalent to k on n, we can write the above equation as shown. Taking the limit n to approach infinity, h to approach 0, and assuming smoothness, one obtain the equation as follows, which is from the definition of a second derivative. KL square on m is the square of the propagation speed in this particular case. In the case of a stress pulse propagating longitudinally through a bar, the bar acts much like an infinite number of springs in series and can be taken as an extension of the equation derived from Hooke's law. A uniform bar that is of constant cross-section made from a linear elastic material has stiffness K given by K is equivalent to EA on L, where A is the cross-sectional area and E is the Young's modulus of the material. The wave equation becomes as shown. AL is equal to the volume of the bar, and therefore AL on M is equivalent to 1 on rho, where rho is the density of the material. The wave equation then reduces to as shown: partial square u x t on partial t square is equivalent to e on rho partial square u x t on partial x square. The speed of a stress wave in a bar is therefore root e on rho as shown. This episode is brought to you by Cisco Educational Premium. Okay, so last week part 1 we looked at something on the wave equation. We introduced ourselves on what the wave equation is, and we looked at example of waves. We went on to look at the wave equation in one space dimension and even derived it. Today I want us to dig deeper into the wave equation, starting with what does it mean? But before we get started, I want you to take a piece of paper and a pen. Oh no, that's even too far. Just down in the comments, type this name, Jean D'Alembert. This is the guy who first solved the wave equation, as we are going to look at. The one-dimensional wave equation is unusual for a partial differential equation in that a relatively simple general solution may be found. Defining new variables, as shown, changes the wave equation into partial square u on partial psi partial eta is equivalent to 0, which leads to the general solution as shown, or equivalently uxt is equivalent to fx minus ct plus gx plus ct. In other words, the solutions of 1D wave equation are sums of a right traveling function f and a left traveling function g. Traveling, and I quote, means that the shape of these individual arbitrary functions with respect to x stays constant. However, the functions are translated left and right with time at a speed c. This was derived by Jean-Laurent D'Alembert. Another way to arrive at this result is to factor the wave equation into two one-way wave equations. From this, V must have the form Gx plus Ct, and from this the correct form of the full solution U can be deduced. The usual second order wave equation is sometimes called the two-way wave equation. Superposition of two waves to distinguish it from the first order one-way wave equation describing the wave propagation of a single wave in a predefined direction. For an initial value problem, the arbitrary functions f and g can be determined to satisfy initial conditions ux0 is equivalent to fx, ut x0 is equivalent to gx. The result is D'Alembert's formula. In the classical sense, if fx in ck and gx in ck minus 1 and utx in ck. However, the waveforms of f and g may also be generalized functions, such as the delta function. In that case, the solution may be interpreted as an impulse that travels to the right or the left. The basic wave equation is a linear differential equation, and so it will adhere to the superposition principle. This means that the net displacement caused by two or more waves is the sum of the displacements which will have been caused by each wave individually. In addition, the behavior of a wave can be analyzed by breaking up the wave into components, like the Fourier transform breaks up a wave into sinusoidal components. Another way to solve the one-dimensional wave equation is to first analyze its frequency eigenmodes. A so-called eigenmode is a solution that oscillates in time with a well-defined constant angular frequency ρ, so that the temporal part of the wave function takes the form and the amplitude is a function fx of the spatial variable x, giving a separation of variables for the wave function. This produces an ordinary differential equation for the spatial part fx as shown, which is precisely an eigenvalue equation for fx, hence the name eigenmode. It has the well-known plane wave solutions as shown. Fx is equivalent to ae plus or minus ikx, that is, it has been raised to that, with the wave number k is equivalent to the total wave function of this eigenmode is then the linear combination shown, where the numbers a, b depend in general on initial and boundary conditions of the problem. Eigenmodes are useful in constructing a full solution to the wave equation because each of them evolves in time trivially. The phase factor E, so that a full solution can be decomposed into an eigenmode expansion as shown, which is exactly in the same form as in the algebraic approach. Functions S are known as the Fourier component and are determined by initial and boundary conditions. These are so-called frequency domain method, alternative to direct time domain propagations such as FDTD method of the wave packet UXT, which is complete for representing waves in absence of time dilations. Completeness of the Fourier expansion for representing waves in presence of time dilation has been challenged by cheap wave solutions, allowing for time variation. The cheap wave solutions seem particularly implied by very large but previously inexplicable residuals in the flyby anomaly, and differ from sinusoidal solutions in being receivable at any distance only at proportionally shifted frequencies and time dilations corresponding to past chip states of the source. The factorial wave equation, from which the scalar wave equation can be directly derived, can be obtained by applying a force equilibrium to an infinitesimal volume element. In an homogeneous continuum, Cartesian coordinate x with a constant modulus of elasticity E, a factorial elastic deflection uxt causes the stress tensor T is equivalent to E del U PA, the local equilibrium of A, the tension force. Diff T is equivalent to del dot E del U is equivalent to E delta U Newton per meter cubic due to deflection um and b, the inertial force rho, partial square u on partial t square Newton per cubic meter, caused by the local acceleration partial square u on partial t square meter per second square, can be written as shown. Rho partial square u on partial t square is minus E delta U is equivalent to 0. By matching the density rho kilograms per cubic meter and elasticity module E, the sound velocity C is equivalent to root E on rho meter per second, results material law. After insertion follows the well-known governing wave equation for our homogeneous medium. Partial square u on partial t square minus c square delta u is equivalent to 0. Note, instead of factorial uxt, only scalar uxt can be used, i.e. waves are traveling only along the x-axis, and the scalar wave equation follows as partial square u on partial t square minus c square partial square u on partial x square is equivalent to 0. The above factorial partial differential equation of the second order delivers two mutually independent solutions. From the quadratic velocity term, c square is equivalent to plus c square is equivalent to negative c square, can be seen that there are two waves traveling in opposite directions. Plus c and negative c are possible. Hence results the designation two-way wave equation. And I quote, it can be shown for plane longitudinal wave propagation that the synthesis of two one-way wave equations leads to a general two-way wave equation. For del C is equivalent to 0, special two-wave equation with the D'Alembert operator resolves as shown. Therefore, the factorial first-order one-way wave equation with waves traveling in predefined propagation direction C resolves as partial u on partial t minus c dot del u is equivalent to 0. A solution of the initial value problem for the wave equation in three space dimensions can be obtained from the corresponding solution for a spherical wave. The result can be also used to obtain the same solution in two space dimensions. The wave equation can be solved using the technique of separation of variables. To obtain a solution with constant frequencies, let us first Fourier transform the wave equation in time as shown. Psi rt is equivalent to integral from negative infinity to infinity psi r omega e raised to negative I omega t d omega. So we get del square plus omega square on c square psi r omega is equivalent to 0. This is the Helmholtz equation and can be solved using separation of variables. If spherical coordinates are used to describe a problem, then the solution to the angular part of the Helmholtz equation is given by spherical harmonics, and the radial equation now becomes shown. Here k and the complete solution is now given as shown, where h sub l 1 kr and h sub l 2 kr are spherical Henkel functions. For example, to gain a better understanding of the nature of these spherical waves, let us go back and look at the case when L is equivalent to 0. In this case, there is no angular dependence and the amplitude depends only on the radial distance. That is, psi rt goes to u rt. In this case, the wave equation reduces to as shown, which can be written as shown, where the quantity Ru satisfies one-dimensional wave equation. Therefore, there are solutions in the form shown, where F and G are general solutions to the one-dimensional wave equation and can be interpreted as respectively an outgoing or incoming spherical wave. The outgoing wave can be generated by a point source, and they make possible sharp signals whose form is altered only by a decrease in amplitude as R increases. Such waves exist only in cases of space with odd dimensions. Although the word monochromatic is not exactly accurate, since it refers to light or electromagnetic radiation with a well-defined frequency, the spirit is to discover the eigenmode of the wave equation in 3 dimensions. Following the derivation in the previous section on plane wave eigenmodes, if we again restrict our solutions to spherical waves that oscillate in time with well-defined constant angular frequency omega, then the transform function RU RT as simply plane wave solutions shown. From this, we can observe that the peak intensity of the spherical wave's oscillation, characterized as the square wave amplitude shown, drops at the rate proportional to 1 on r square, an example of the inverse square law. The wave equation is linear in nu and it is left unaltered by translations in space and time. Therefore, we can generate a great variety of solutions by translating and summing spherical waves. Let phi be an arbitrary function of three independent variables, and let the spherical waveform f be a delta function. That is, let f be a weak limit of continuous functions whose integrity is unity, but whose support, the region where the function is non-zero, shrinks to the origin. Let the family of spherical waves have center, and let r be the radial distance from that point. Thus, we get the equation as shown. If U is a superposition of such waves with weighting function psi, then we get as shown, and the denominator 4 pi c is a convenience. From the definition of the delta function, U may also be written as shown, where alpha, beta, and gamma are coordinates on the unit sphere S, and omega is the area element on S. This result has the interpretation that UTX is T times the mean value of phi on a sphere of radius Ct centered at X, as shown, and it follows as in the equations. U 0xyz is equivalent to 0, ut 0xyz is equivalent to phi xyz. The mean value is an even function of t, and hence if vt xyz is equivalent to partial on partial t mct psi, then v0 xyz is equivalent to psi xyz, vt 0 xyz is equivalent to 0. These formulas provide solution for the initial value problem for the wave equation. They show that the solution at a given point P, given t xyz, depends only on the data on the sphere of radius Ct that is intersected by the light cone drawn backwards from P. It does not depend upon the data on the interior of this sphere. Thus, the interior of the sphere is lacuna for the solution. This phenomenon is called Huygens principle. It is true for odd numbers of space dimension, where for one dimension the integration is performed over the boundary of an interval with respect to the Dirac measure. It is not satisfied in even space dimensions. The phenomenon of lacunas has been extensively investigated in Thibaut and Ding, 1970-1973. Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals. This episode is brought to you by Cisco Educational Premium. We have peered into the wave equation and now we are deep in the middle of it. We already introduced the wave equation, derived it, and even studied it in different space dimensions. So we can comfortably say that we know what this guy means and how relevant it is. But just in case you need to brush up on some of the concepts, feel free to check on our earlier episodes on this. Today we will just wrap everything up, starting with the scalar wave equation in two space dimensions. In two space dimensions, the wave equation is ut is equivalent to c square uxx plus uyy. We can use the three-dimensional theory to solve this problem if we regard u as a function in 3 dimensions that is independent of the third dimension. If u 0xy is equivalent to 0, ut 0xy is equivalent to phi xy, then the three-dimensional solution formula becomes as shown, where alpha and beta are the first two coordinates on the unit sphere, and d omega is the area element on the sphere. This integral may be written as a double integral over the disk D with center xy and radius ct. As shown, this apparent that the solution at txy depends not only on the data or on the light cone, where x minus psi square plus y minus nu square is equivalent to c square t square, but also on data that are interior to that cone. We want to find solutions to utt minus delta u is equivalent to 0 for u Rn times 0 infinity going to R, with ux 0 being equivalent to gx and ut x0 be equivalent to hx. In odd dimensions, assume n is greater or equal to 3 is an odd integer, and g in cm plus 1 Rn, h in cm Rn for m is equivalent to n plus 1 on 2. Let gamma n be 1 times 3 times 5 and so on, n minus 2. And let u xt be as shown. Then we have utt limit of xt is the approach x00, and limit xt is the approach x00 as shown. In even dimensions, we assume n greater or equal to 2 is an even integer, and g in cm plus 1 Rn, h in cm Rn for m is equivalent to n plus 2 on 2. Let gamma n be equivalent to 2 times 4 times and so on to n, and let uxt be as shown. Then new utt limit as xt approaches x raised to 0 and limit as xt approaches to x raised to 0 and 0 be as shown. Let us look at reflection and transmission at the boundary of two media. For an incident wave traveling from one medium where the wave speed is c1 to another medium where the wave speed is c2, one part of the wave will transmit into the second medium while another part reflects back into the other direction and stays in the first medium. The amplitude of the transmitted wave and the reflected wave can be calculated by using the continuity condition at the boundary. Consider the component of the incident wave with an angular frequency of omega, which has the waveform as shown. At t is equivalent to 0, the incident reaches the boundary between the two media at x is equivalent to 0. Therefore, the corresponding reflected wave and the transmitted wave will have the waveforms as shown. The continuity condition at the boundary will be as shown and gives the equations A plus B is equivalent to Z, A minus B is equivalent to K2 on K1C is equivalent to C1 on C2C. And we have the reflectivity and transmittivity as shown. B on A is equivalent to C2 minus C1 on C2 plus C1. C on A is equivalent to 2C2 on C2 plus C1, where C2 is less than C1. Then the reflected wave has a reflection phase change of 180 degrees. Since B on A is less than 0, the energy conservation can be verified by B square on C1 plus C square on C2 is equivalent to A square on C1. It only holds true for any component regardless of its angular frequency omega. The limiting case of C2 is equivalent to 0 corresponds to a fixed end, and I quote, that doesn't move. Whereas the limiting case of C2 approaching infinity corresponds to a, and I quote, to a free end. A flexible string that is stretched between 2 points x is equivalent to 0 and x is equivalent to L satisfies the wave equation for t greater than 0 and 0 less than x, which is less than L. On the boundary points, you may satisfy a variety of boundary conditions. A general form that is appropriate for applications is as shown: minus ux t0 plus au t0 is equivalent to 0, ux tl plus bu tl is equivalent to 0, where a and b are non-negative. The case where u is required to vanish at endpoint, that is fixed end, is the limit of this condition when the respective a or b approaches infinity. The method of separation of variables consists in looking for a solution of this problem in the special form utx is equivalent to tt vx. A consequence is that t double prime on c squared t is equivalent to v double prime on v is equivalent to negative lambda. The eigenvalue lambda must be determined so that there is non-trivial solution of the boundary value problem as shown. It is a special case of the general problem of the Sturm-Liouville theory. If A and B are positive, the eigenvalues are all positive, and the solutions are trigonometric functions. A solution that satisfies square integrable initial conditions for u and ut can be obtained from expansion of these functions in the appropriate trigonometric series. Approximating the continuous string with a finite number of equidistant mass points, one gets the physical model as shown. If each mass point has the mass m and the tension of the string is f, separation between the mass point is delta x, and mu I is equivalent to 1 to n, are the offset of these endpoints from their equilibrium points. That is their position on a straight line between the two attachment points of the string. The vertical component of force towards point I plus 1 is as shown: ui plus 1 minus ui on delta x f. And the vertical component of the force towards point R minus 1 is ui minus 1 minus ui on delta x f. Taking the sum of these two forces and dividing with mass m, one gets for the vertical motion as shown. As the mass density is rho is equivalent to m on delta x, this can be written as shown. The wave equation is obtained by letting delta x to approach 0, in which case uit takes the form uxt, where uxt is a continuous function of two variables. Ui takes the form partial square u on partial t square, and ui plus 1 plus ui minus 1 minus 2 ui on delta x square approaches partial square u on partial x square. But the discrete formulation of the equation of state with a finite number of mass points is just the suitable one for a numerical propagation of the string motion. The boundary condition u 0t is equivalent to ult is equivalent to 0, where L is the length of the string takes in discrete formulation the form for the outermost points u1 and un. The equations of motion are as shown, while for 1 less than I less than n is as shown, where C is equivalent to root F on rho. If the string is approximated with 100 discrete mass points, one gets the 100 coupled second order differential equations, or equivalently 200 coupled first order differential equations. Propagating these up to the terms L on C, K 0.05, K is equivalent to 0 to 5. Using an 8th order multi-step method, the 6 states can be displayed, shown. The red curve is the initial state at time 0 at which the string is let free in a predefined shape with all u.i is equivalent to 0. The blue curve is the state at time L on C 0.25, that is after a time that corresponds to the time a wave that is moving with the nominal wave velocity c is equivalent to root f on rho would need for 1/4 of the length of the string. We have the figure displaying the shape of the string at times L on ck 0.05, k is equivalent to 6 to 11. The wave travels in direction right with speed c is equivalent to root f on rho without being actively constrained by boundary condition at the two extremes of the string. The shape of the wave is constant, that is, the curve is indeed of the form fx minus ct. There is a figure displaying the shape of the string at the terms L on ck 0.05, k is equivalent to 12 to 17. The constraint on the right extreme starts to interfere with the motion, prevent the wave to raise the end of the string. The figure displaying the shape of the string at the terms L on ck 0.05, k is equivalent to 18 all the way to 23, when the direction of motion is reversed. The red, green, and blue curves are the states at the terms L on ck 0.05. K is equivalent to 18 all the way to 20, while 3 black curves correspond to the states at terms L on ck 0.05. K is equivalent to 21 all the way to 23, with the wave starting to move back towards left. There are figures finally displaying the shape of the string at terms L on ck 0.05, k equivalent to 24 all the way to 29, and L on ck 0.05, k is equivalent to 30 all the way to 35. The wave now travels towards left, and the constraints at the endpoints are not active anymore. When finally they are at the extreme of the string, the direction will again be reversed in a way similar to what is displayed in the figure. The one-dimensional initial boundary value theorem may be extended to an arbitrary number of space dimensions. Consider a domain D in a m-dimensional X space with boundary B. Then the wave equation is to be satisfied if X is in D and t greater than 0. On the boundary of D, the solution U shall satisfy partial U on partial N plus AU is equivalent to 0, where N is the unit outward normal to B and A is a negative function defined on B. The case where u vanishes on B is a limiting case for A approaching infinity. The initial conditions are u 0x is equivalent to fx, ut 0x is equivalent to gx, where f and g are defined in D. This problem may be solved by expanding f and g in eigenfunctions of the Laplacian in D, which satisfy the boundary conditions. Thus, the eigenfunction nu satisfies del v plus lambda v is equivalent to 0 in D, and partial v on partial n plus av is equivalent to 0 on B. In the case of two space dimensions, the eigenfunctions may be interpreted as the modes of vibration of a drumhead stretched over the boundary B. If B is a circle, then these eigenfunctions have an angular component that is trigonometric function of the polar angle theta multiplied by a Bessel function of integer order of the radial component. If the boundary is a sphere in three space dimensions, the angular components of the eigenfunction are spherical harmonics, and the radial components are Bessel functions of half integer order. The inhomogeneous wave equation in one dimension is as the following: utt minus c square uxx xt is equivalent to sxt, with initial conditions given by ux0 is equivalent to fx, ut x0 is equivalent to gx. The function sxt is often called the source function because in practice it describes the effects of the sources of waves on medium carrying them. Physical examples of source function include the force driving a wave on a string, or the charge or current density in the Lorentz gauge of electromagnetism. One method to solve the initial value problem is to take advantage of a special property of the wave equation in an odd number of space dimensions, namely its solutions respect causality. That is, for any point xi, ti, the value of uxi, ti depends only on the values of fxi plus cti and fxi minus cti, and the values of the function gx between xi minus cti and xi plus cti. This can be seen in D'Alembert's formula that has been shown, where these quantities are the only ones that show up in it. Physically, if the maximum propagation speed is c, then no part of the wave that can't propagate to a given point by a given time can affect the amplitude at the same point and time. In terms of finding a solution, this causality property means that for any given point on line being considered, the only area that needs to be considered is the area encompassing all the points that could causally affect the point being considered. Denote the area that causally affects point xiti as Rc. Suppose we integrate inhomogeneous wave equation over this region as shown. To simplify this greatly, we use Green's theorem to simplify the left side to get as shown. The left side is now the sum of three line integrals along the bounds of the causality region. These turn out to be fairly easy to compute. In the above, the term to be integrated with respect to term disappears because the term interval involved is 0. Thus, dt is equivalent to 0. For the other two sides of the region, it is worth noting that x plus or minus ct is a constant, namely xi plus or minus cti, where the sign is chosen appropriately. Using this, we can get the relation dx plus or minus c dt is equivalent to 0. Again, using the right sign, we get as shown. And similarly, for the final boundary segment, we get as shown. Adding the three results together and putting them back in the original integral, we obtain the equation Solving for uxiti, we arrive at uxiti as shown. The last equation of the sequence, the bonds of the integral over the source function, has been made explicit. Looking at this solution, which is valid for all choices xiti compatible with the wave equation, it is clear that the first two terms are simply D'Alembert's formula, as stated as a solution of the homogeneous wave equation in one dimension. The difference is in the third term, the integral over the source. For one-way propagation, that is, waves are traveling in a predefined direction, plus C or negative C in homogeneous media. Wave propagation can be calculated with a tensorial one-way wave equation, resulting from factorization of the vectorial two-way wave equation, and an analytical solution can be derived. In 3 dimensions, the wave equation, when written in elliptic cylindrical coordinates, may be solved by separation of variables, leading to the Matthew differential equation. The elastic wave equation, aka Navier-Koch equation, in 3 dimensions describes the propagation of waves in isotropic homogeneous elastic medium. Most solid materials are elastic, so this equation describes such phenomena as seismic waves in Earth and ultrasonic waves used to detect flaws in materials. While linear, this equation has a more complex form than the equations given above, as it must account for both longitudinal and transverse motion. By using del cross u is equivalent to del dot u minus del dot u is equivalent to del dot u minus del u. The elastic wave equation can be written into more common form of Navier-Koch equation. Note that in the elastic wave equation, both force and displacement are vector quantities. Thus, this equation is sometimes called the vector wave equation. You can see that if f and del dot u are set to 0, this becomes Maxwell's equation for the propagation of the electric field E, which has only transverse waves. In dispersive wave phenomena, the speed of propagation varies with wavelength of the wave, which is reflected by a dispersion relation. Omega is equivalent to omega k, where omega is the angular frequency and k is the wave vector describing plane wave solutions. For light waves, the dispersion relation is omega is equivalent to plus or minus c absolute value of k, but in general, the constant speed c gets replaced by a variable phase velocity v. P is equivalent to omega k on k. Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So how do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.